Image creation and what happens with an X-ray beam as it impacts the image receptor is most complicated, and the way the image is formed is most complicated portion of the curriculum. And because of that, we cover it more than anything else. So what we're gonna do is we're gonna cover it this semester in depth, and it's gonna get kind of tedious. I'm not gonna lie to you, it's gonna get kind of tedious. There's only going to be 4 tests. One of those is going to be a review from last semester, and hopefully you've retained enough from last semester that test, I won't say it won't be challenging, but because it's challenging information last semester, but hopefully it'll act as a little bit of a grade inflator. But then once we get into the content for this semester, we're going to go into a deep dive. So Amy kind of touched the surface of it. This semester we're going to go into a deep dive. Then summer semester is all about modalities as far as my class goes. But whenever we come back in the fall, we're going to hit it again. The first time we hit it, we're going to hit it hard. And so a second deep dive into it. And then we're going to go back through it again in the fall semester as kind of a review. So we're going to cover it twice in the fall semester. So that's 4 times that we're covering this throughout the curriculum because it is so difficult. And it would seem like it has become easier. Back in the day when we used screens and films to make our images, we had to know the composition of the screens themselves and what was inside the screens to make them, the chemical composition and the actual phosphors inside the screen to make the image. We also had to know exactly what the chemical composition of the film was as well. And we had to know how kVp affected it and how mass affected it and all that. And it would seem like that has become easier, and it should have become easier in that we also had to know the chemical composition of the processing chemistry. So we had to know all this stuff that really amounted to a hill of beans, to be frank about it. We had to know all this stuff that really didn't matter, and now we don't anymore. But it's not easier. And the reason it's not easier is because the computer has taken over a lot of what we had to visualize and learn. And there was immediate feedback in clinicals. If you overexposed or underexposed a patient or used improper kVp, you saw an immediate effect of that. So you could diagnose your image. Now the computer kind of fixes all that stuff. We still have to know what those interactions are on the patient, what the remnant beam looks like, but we don't have that immediate feedback. You completely mess up your technical factors and you still get a good image. Use too high kVp doesn't affect much. Use too low a kVp might, if you really mess it up, but within a certain range that you should already be familiar with, it just looks the same, right? So it's not any easier to learn it, and in a lot of ways it's more complicated to learn it because you have to have all this knowledge that you can't really see the effects of. Does that kind of make sense? So a lot of what we're going to be talking about, when you make an exposure on the image, you're not really going to see a whole lot of difference between them, but you have to know it for the registry and also for radiation protection for the patient. You have to know good technique and accurate kVp and mass values so that you don't overexpose the patient or underexpose the patient and send a bad image to the radiologist he can't make a diagnosis off of. So that's where we're going to spend the rest of the semester. And you may be thinking, well, why not just jump into the new material? Well, in order to fully understand what's going on at the image receptor and how the remnant beam coming through the patient is going to affect the construction of that image, you have to know what the patient's doing to the beam that hits them. Does that kind of make sense? So you have to know the interactions inside of the patient, which Amy's going to go through in depth this semester, and we're going to look at what the remnant beam looks like, the remnant beam being the image forming beam. So we got to know what's going on with the patient, pathology, body habitus, the types of tissues that we're going to be penetrating, what's going on with each one of those. But to understand that, we have to know what's coming out of the x-ray tube, right? So we have to know the quantity and quality of x-rays that we're emitting from the x-ray tube in order to know what's going into the patient, so we know what's coming out of the patient. So to understand that, then we have to remember what's happening as we change our technical factors. We increase or decrease our kVp and our mass, so that we know what's coming out of the x-ray tube, what's being created in the x-ray tube, and therefore what's coming out of the x-ray tube, how we affect each one of those. So it's important to review and remember those things before we get into the new material in the image creation. And it's been a month, right, since we talked about any of this stuff. So it bears repeating. This is cool. Apparently we covered it all already.
Wow.
Let me try all over again. There we go. All right. So what we're doing this semester is, again, 6 through 10. Then we're going to jump. The chapters used to be sequential before we went to CR and DR, so we're going to be kind of all over the textbook. So what we're going to do is we're going to talk about all this stuff, 6 through 10, and we're going to have a test over that, and then we're going to talk about chapters 15 and 16, which are really your technical factors, and what it is that we do that controls our quantity and quality. We'll have a test over that. We'll talk about specifically image quality, different types of resolution, what controls that resolution. So it's really kind of sharpness, recorded detail, visibility functions, and then we'll have a test over that. And then we'll talk about building on that. We'll talk about control scatter radiation, what we can do to enhance the image, reduce patient dose, and reduce unwanted signal to the image receptor, and we'll have a test over that as well. And then we'll have a final exam. Okay, so if we have some time, we'll touch throughout the semester on computed and digital radiography, but if we have time in class, we'll cover some CR and DR as well. We'll definitely get to that in the fall semester. So you do have homework assignments here as well. Your homework assignments actually have a little bit of teeth to them, so your homework assignments count about 10%, or count 10% of your test grade, but everything else is the same. Okay? So keep up with your homework assignments. You should be able to access those and see them in your assignment tab. Apparently the computer's left for the weekend already. So just locate them in your assignment tab and just keep up with them. If you get behind, you miss an assignment or whatever at the end of the semester, if it looks like it might affect your grade, substantially, I can open them back up. All right, any questions on what we're doing this semester? No? Grading? Anything? Okay, good. All right. So imaging system, we're going all the way back to chapter 6, and I'm just going to leave this open so that you can see the notes down at the bottom. If I put it in presenter mode, then those go away. So just to make sure I don't miss something, and also you can see the notes, I'm just going to leave it open like that. So the imaging system, we identify the imaging system, if you remember, by a couple of different things, one being energy level and the other being use. So the most common example of use that you see is fluoroscopy versus radiography, right? So in some rooms you have what we refer to as an RF room, and that is both, right? It can do both. You've got two x-ray tubes in those types of rooms, one inside of the table and one outside of the table. That's an RF room. And some of your rooms are just straight diagnostic rooms. They don't have any kind of fluoroscopy. But we almost have to go outside of diagnostic radiology and get into some of the modalities to get to different energy levels. Mammo, the only thing we're shooting in mammo is soft tissue. The higher the kVp, the more scatter we create. So we don't want to use high kVp for mammo. We want to use lower kVp, so your mammo system is going to be lower kVp. So in that, we've got, and regardless of if it's a RF room or just a straight radiography room, we have to have the image receptors, and we have to have, with one exception, that y'all are going to see. A really cool system that we added a clinical site at Azalea Orthopedics. So if you've, y'all been to clinicals already. So anybody seen Azalea Orthopedics on their, have you been over there yet?
That's where I'm at right now.
Okay, that's where you are now. Have you seen the spaceship?
The
Yeah, that I've never seen anything like that. So this is a thing that you stand up in, and I spent 10 minutes looking at it, so I don't really know its capabilities, but it's kind of scans, doesn't it? Kind of like a CT type thing.
Like, you don't really see the arms, but like from here all the way down, it scans like the whole body.
Yeah. So they can do. If you've ever had a CT, you lay on the couch of the CT, and before the CT begins, in a lot of cases, it'll just pull you through the CT, and it takes what they call a topogram. It's a all-over body X-ray, and they pull you back out of it, and they start making the cuts, right? And so the topogram is kind of like what that thing does. It just kind of scans your entire body. It's wild. I've never seen anything like it. All of the faculty went over and took a tour of the place. I'd never seen it. They were talking about this spaceship thing. Y'all are kind of on crack. I walked in, I said, kind of looks like a spaceship. So anyway, you'll see it. It's pretty cool. So aside from something like that, you're going to have something to lay down on. We'll call that the couch. The table is what we usually refer to it as. So you remember the characteristics of the tabletop. The first thing is it has to be radiolucent, right? Remember that we don't have anything that's radioparent, just different levels of radiolucency. So it not only has to be radiolucent, but it also has to be uniform thickness. If we're radiolucent and thin at one end and radiolucent and thick at the other end, then what we're going to have is more absorption on the thick end than what we have on the thin end. So it has to be uniform thickness, plus it has to be radiolucent. So those are characteristics of that. You have to have a way of moving it around. And we talked about those last semester. Some of them are motor driven. Most of those are going to be your fluoroscopy rooms. And some of them will be free floating, kind of like what we have down in the lab. And most of the time, those are going to be your just diagnostic rooms. So then in the system, of course, we've got three parts. We've got the tube, the console, and the high voltage generation system, which we're going to look at individually. So the console is what you're most familiar with, and it's where you control everything. And in everything, pretty much we're going to break that down into a couple of different things, and providing we're not including sharpness, recorded detail into that. Quantity and quality. So quantity is anything that increases or decreases the number of x-rays that we create. And most of the time when we're thinking about quantity, we're thinking about two things, and that is MA and time. We're going to get deep into kVp here in a minute, and that's probably what we're going to finish with today is kVp. But if you remember, we finished last semester with a discussion of the Brim spectrum. You remember that? There's that funny little bell curve, and the creation of x-rays at the target versus the emission from the x-ray tube. So we're going to take a look at that pretty much in depth, but when we think of quantity, what we use primarily to control quantity is MA and time, so overall mass. But kVp, if you remember from last semester, kVp affects quantity even more so than what mass does. You double your mass, and you double your exposure to the patient, you double your exposure to the image receptor. How much of a change in kVp do you need to double the exposure to the image receptor? 15%. 15% is all it takes, right? So it's significant. And then quality is all about kVp, sort of, right? So quality is peak energy, certainly, but it's also what prevents low energy X-ray photons from just absorbing inside of the patient. So if you remember all the way back, this would be all the way back to August, you know, we talked about how unsafe X-rays were originally, and some of the stuff that we did to make it safer. One was the ability to create higher kVp, but the other was to get rid of some of those low energy X-ray photons, and we used what to do that? Somebody said it, I think. Filtration, right. So thin sheets of aluminum to remove some of those low energy X-ray photons. So that affects quality as well. So we also talked about the best measures, or the measures of quality, kVp being one, and that's what we use to control our quality. The filtration, remember, we've got two different types. We've got inherent filtration, and that's what we can't remove from the system, right? Because either the system won't work, or legally we can't remove it from the system. Inherent filtration is anything that brings our filtration up to 2.5 millimeters of aluminum, providing we're shooting above 70 kVp, right? So the better measure of quality, kVp is a measure of quality. Quality is affected by kVp, it's affected by filtration as well, but the better measure of quality is your half value layer, right? And you kind of remember the little math thing that I ran through, comparing two different rooms, brand new room versus an older room. The older room would have more inherent filtration because of tanning of the X-ray tube. All right, so other things that we control would be our line voltage compensation. We really don't control that unless you're working off of an old single-phase system. You're just not going to see that. It's going to be built into the system. You can do a Google search, and you can find a control panel where it actually has line voltage compensation on the control panel. But in any three-phase or high-frequency room, you're just not going to see that. It's built into the system. It's still there. And what that was, if you remember, is it's kind of inaccurate to say surge protector, because it protects against both surges and dips in incoming line voltage. So it's more like a battery backup, so that it maintains a constant kVp, so that when you make your exposure, you know exactly what kVp you're using. We also select our photocells, or our automatic exposure. You don't really select your generator type. That's going to be just your machine. But you can select your focal spot being what we primarily use to affect a change in sharpness or recorded detail. And then you don't really select your filtration either. I have worked with systems where you could, on the X-ray tube itself, change your filtration. But those, I think those machines were kind of remnants of what we used to use before we had dedicated mammography machines. I haven't seen that capability in an X-ray tube in 30 years. Dating myself again. All right, so intensity, where we are talking about quantity, we're talking about intensity. And with mass, that's going to be a direct relationship. Whenever we change our mass, there's a direct relationship. Double your mass, you double your image receptor exposure. And we're going to talk pretty in-depth this semester about how we get to different mass values, or the same mass values using different factors, and how to adjust our mass, to compensate for certain things. And then quality, again, is going to be our kVp. Half value layer is better measure. Generator type does affect it, but you can't really control that unless you change different rooms. All right, so we just talked about that. We'll talk about kVp selection here. All right, so on the console with our kVp manipulation, you push the buttons to increase or decrease kVp. What device are you actually manipulating in order to truly make the change in kVp? Auto transformer, right, so the auto transformer, the voltage comes out of the, line voltage compensation, first thing it goes into is auto transformer. Primary side versus secondary side. Primary side means the side that we supply the voltage to, right? We're using alternating current. Alternating current creates a changing magnetic field. And then what we're actually adjusting are the contacts on the secondary side. So we squeeze those secondary side contacts together and our voltage goes down. We spread them out and they go up, right? So the more contacts on the secondary side of the auto transformer, the higher the voltage. So we don't have kilovoltage yet, but that's our kilovoltage control. Our auto transformer is our kilovoltage control, all right? We don't have kilovoltage until it goes into the step-up transformer, high voltage transformer, exactly. So with the auto transformer, we have one coil, right? And it uses the principle of self-induction. It has to have alternating current. We can't use it without alternating current, so it has to have alternating current. Works off transformer law. And what we're actually doing is adjusting our voltage by manipulating those contacts on the secondary side. So the turns ratio is variable. You can change it, you can increase it or decrease it. And we have, if you remember, almost all of the meters and controls are found on the low voltage side for safety, including the kVp meter. We call it a pre-reading kVp meter because it's not kVp yet. But what kind of turns ratio do we have on the high voltage transformer? Is it variable or is it set? High voltage transformer is set. It's set, right? So it doesn't change. So based on transformer law, we know how much of a change we're going to have between the primary and secondary side. It's always going to be the same proportion, right? So if we fix our voltage at, and even before the auto transformer, we send it through the line voltage compensation circuit, and then we put it into the auto transformer. If we know what's coming out of the secondary side of the auto transformer, we know what our voltage is going to be, right? So we have to have a way of reading that, and this with our pre-reading kVp meters. Pre-reading because we don't have kVp yet. It's just we know what that voltage is going to be once we send it through. All right? It's starting to make a little, or sound familiar? Okay, so if intensity is mass, kVp is our quality, it controls a lot of different things. So in the X-ray tube, what we've got is the potential difference between the cathode end and the anode end of the X-ray tube, right? So once you hit prep, you don't have tube voltage yet. What you've got is just heating of the filament to create a space charge, right? So you create a space charge, but you don't have tube current yet. You just have filament current. So once you press your exposure button, now you activate the high voltage portion and you send the electrons across the tube. Now you truly have tube current, right? So what it controls in the X-ray tube is that potential difference between the cathode end of the X-ray tube and the anode end of the X-ray tube. The difference then between 50 kVp and 100 kVp is the difference in that charge. So the higher the kVp, the faster those electrons travel from cathode to anode, right? So the only thing that you're really changing inside the X-ray tube whenever you increase your kVp is the speed of those electrons as they travel across the tube. Now you're going to run into questions that you know, I won't say they're they're tricky. I'm not saying they're trying to trip you up, but they are trying to make sure that you're paying attention. The speed of the electrons change, but all the photons travel at the same speed, and that will be the speed of light, right? So really the difference in the X-ray photons then becomes frequency and wavelength. Remember talking about that last semester. So frequency kind of follows the energy. The higher the frequency, the higher the energy. Higher kVp, higher frequency. shorter wavelength. So the squiggly lines get more squiggly the higher the kVp, right? So two potential difference, electric potential, quality of the X-ray beam is everything that we call kVp. When kVp is adjusted, when we increase kVp, then we change the attraction between the cathode and the anode. That changes the speed of the electrons. Whether you want to think of kVp as being a pulling force from the target or a pushing force from the anode or from the cathode, it really doesn't matter which perspective you want to consider that. But they travel across. The higher the kVp, the higher the speed. And the result is that the higher the kVp, the more we can penetrate. Since what we're trying to do is get penetration through the patient so we can see a shadow of their anatomy, an X-ray beam that doesn't penetrate has what kind of quality? Good, high, or low? It's low, right? So kVp is our quality, is what we use to control our quality. All right, so it increases penetration, and also if we don't do anything else, and this is the tricky part of kVp, when we get later in the semester and we'll talk about technique changes, if the only thing that you do is change your kVp, then your patient dose and the dose to the image receptor will increase, right? It's not until we use that 15% rule where we maybe increase kVp and reduce mass that our image receptor exposure remains the same and patient dose actually decreases a little bit. So we'll get there later in the semester. Okay. So we just pretty much talked about all that. So the effect on the image, though, let's back up a little bit. We didn't talk about all of it. So how does it affect interactions? As kVp increases, we say, and we're going to get deeper into this later in the semester, but as kVp increases, what happens to the interactions inside of the patient? What does kVp control? Penetration, right? So it controls penetration. So as kVp increases, penetration increases, right? As far as image receptor exposure goes, that does come with a little bit of a, I don't really want to say hazard, but it does come with a downside. And that is that the scatter radiation that you create inside of the patient is probably also going to be more likely to penetrate, right? So you're going to have more scatter radiation forward to the image receptor. Because of that, in a lot of cases, what we'll say is as kVp increases, scatter increases. Okay. So what we get then is if the only thing that we change is kVp, if we increase kVp, we're going to get more output from the X-ray tube. We're going to get more interactions in the patient. We're going to get more interactions at the image receptor. How's that going to affect our image? And that's the hard part for y'all in this digital age. At the image receptor, it affects a lot. But the actual displayed image, you just don't see a whole lot. You just don't see a whole lot. So all this stuff that we talk about, you can't visualize. All right. The only way that you're going to get an indication that you overexpose the patient using kVp is one thing. Unless you do something really, really dumb, you use 120 kVp for a finger. That would be dumb, right? But aside from that, what's the only indication that you're going to get that you overexpose the patient? That's number. The index number, that's it, right? So it's really, really important that y'all understand techniques so that you know how to kind of police your own, routine and your own images. So the effects on the images are usually pretty minimal. So kVp and the spectra. All right, so this is the part where we're going to run through. I'll kill these. Kind of an introduction, a reintroduction to the brim spectrum. All right, so when we're talking about the brim spectrum, we're talking about the emission spectrum. All right, so we've got creation, we have emissions, and they're nowhere near the same. When we make X-rays, if you recall, what we're shooting is an electron. For our purposes, the smallest portion of the atom. It's not, but for our purposes it is. So the smallest portion of the atom, we're shooting electrons at other electrons. All right, so if you remember back to your atomic numbers, atomic mass numbers of individual particles inside the atom, what was the electron?
-1.
It was 0, right? It really didn't have any mass, any weight. It was 0. And then I think you were thinking -1 because the other two were 1,
Maybe.
right? So your proton and your neutron had a mass of 1. So those are your nuclei, or the subatomic particles in the nucleus, right? So I just drew that much larger than what I expected to or wanted to. So what we've got then is in creation of the X-rays, if you recall, we have two different ways that we created an X-ray. One is if we can shoot this electron close enough to the nucleus of the atom. We used a lot of analogies last semester. It's kind of like, you know, an asteroid getting close to a planet. What's going to happen?
Gravity.
Gravitational pull is going to have an effect on it. So if that electron gets close enough, it's going to change directions. And with that change of direction, what we're going to have is a loss of energy, right? And we talked about the laws of conservation of energy, conservation of matter. We talked about all that last semester. So we said that energy really doesn't go away, right? We just transform it. So you're driving along and you just whip the wheel on your car, and providing you don't roll over, what's going to happen to your car? You're going to be driving at the same speed? It's going to slow down, right? Your tires on the road are going to provide some sort of increased friction. You're going to slow down, right? So the same thing's going to happen here. If we fire this at the target with 100 kVp worth of energy, and it changes direction, and it loses exactly 50 kVp worth of energy, then we create an X-ray photon that's equivalent to the difference, mathematically, subtraction, the difference between those. And so we would create a 50 kVp X-ray photon. The closer we get to the nucleus of the atom, the more we lose, and the higher that is going to be, right? And we had a word for that. There's a German word for slowing down, and that would be brims. And then the second way would be that we have orbital electrons, and if we shoot an electron and it hits an orbital electron and knocks it out of place, then that's going to be a condition that atom is not going to like, right? So it ejects that electron, and it's going to be replaced either by an electron from a different shell, it's going to pop into place, or maybe a free floating electron is going to pop into. This one might wrap back around and snap into place. And what we're going to have then is an X-ray photon that's equivalent to the binding energies between that atom and this atom. And we call that interaction characteristic. Characteristic. So it's characteristic X-ray creation, and it's characteristic specifically of the, you get lost in spelling while you're talking, so, you know. And it's characteristic of the tungsten atom, right? So we changed the atom type, and we're going to change that up. So those are two different means of creation, and they say statistically, then that's 85% of our beam, and then this accounts for the remaining 15%. But overall, the likelihood of any of that happening is really pretty low. And what they say is that at maybe 70 kVp, only about 1% of our the electrons that we send across the tube are gonna result in this. The rest become heat, right? So the main thing that creates heat. So, but if you remember, we kind of walked through this last semester. We use milliamps, and an amp is 6.3 times 10 to the 18th power or something like that, electrons. That's a lot of electrons, right? So even if we use only 1/1000th of that, we still got a lot of electrons. And if only 1% of that becomes X-rays, that's still a lot of X-rays, right? So it's a numbers game. So now, then, with that in mind, we've got two different ways to create X-rays, and only a few, well, a small percentage of the electrons we send become X-rays. Then, with that in mind, also, the majority of the X-rays we create are going to be very low energy, okay? Because what we're shooting, if we're looking for Brim's interaction, what we're shooting is something that's so small that we don't even give it a mass. So it's so small it almost doesn't exist. That's something that's so small that it has mass of 1, meaning it's so small we can't see it, right? So the likelihood of getting close enough to even getting a Brim's X-ray is low. The likelihood of getting a good Brim's X-ray is also low. So most of the X-rays that we create are going to be very low energy, and our Brim spectrum at our X-ray spectrum at our target looks like this, right? So this is before it goes, through the tube and exits and becomes our primary beam. So low, and what we have here is our kVp, and this is our numbers. Right? So the area under this line just represents numbers. The area where these two lines intersect is your peak energy. All right, so we had a couple of things. One is that in the characteristic spectrum, we could create X-rays in, I think it's somewhere around 20 different energy levels. But we only recognize one, right? Rest of them, for our purposes, we just don't really care about. So, what was the one that we're interested in, that we record? You remember? Specific energy level. Somebody said 69, right? So 69 kVp. So if you set 68 kVp on your control panel, and your machine is actually working accurately, then you don't have a characteristic spectrum. If you recall, let's say this X-ray beam here is maybe, we'll say 60 kVp. If you recall, our characteristic spectrum is going to be recognized as just a little spike, right at 69 kVp. So at 60 kVp, we don't have a characteristic spectrum. If I increase my kVp then to 70 kVp, so this is at 60 here, if I increase my kVp to 70, I can't draw a straight line either, 70 kVp, then our characteristic spectrum is going to look, or our X-ray spectrum is going to look like that. So now this is at 70 kVp, and we've got this little spike right there, right? A spike represents 69 kVp. So if you are looking on a test question, and the test question shows you two Brim spectrums, which this is not finished yet, two Brim spectrums, and it says, what can you tell me about these two different spectra? And one has that little ink there, and one does not, then what could you say about those two? They're not drawn like this, but one's on top and one's on bottom. Then we could say this one is
stronger.
Yeah, it's above 69 kVp, right? Because it's got a Brim spectrum. All right, so our kVp, whenever we increase our kVp, this is what we get. So This area under here just represents numbers, so how much of a change did we get from 60 to 70 kVp, which is about, 15%. How much of a change did we get? Just in a word. A lot, right? So we got a great increase in number, we got an increase in peak energy, and we've got a representation of the brim spectrum. This is not what you expose a patient to. This is basically what rotted Edison's lab assistant's hands off, right? So along comes Rollins with his filtration, and we add filtration, some of which is just built into the system. So what's the first thing the X-ray beam hits before it gets to the patient?
The filtration.
Is filtration, but specifically it's a portion of the inherent filtration, but there is a structure that it's got to hit. The tube, the glass or metal envelope, right? So it's not radio parent, it's radio lucent, meaning it's going to absorb some of these X-rays, right? So notice the only thing that changed was minimum energy, right? So what's the second thing that it hits? What's outside of the tube but inside of the housing to help cool the tube? Oil, right. So what's oil? It's liquid grease, pretty much, right? So, basically fat, right? So do you absorb X-rays? Nobody in here completely lean. You absorb X-rays? Some of us are less lean than others, but yeah, you do. So are we going to get some absorption in that oil? And the answer is yeah. So more inherent filtration. Now our brim spectra look like that. So what's the next thing it gets to? Dustin off.
The aluminum?
The port, the aluminum port that holds the oil into the housing. So aluminum is going to absorb some X-rays, and now we've got something that looks more like that. Right? Now there's one more thing that it's going to go through, and it's the thing that enables you to see the light. The mirror, right? Remember, the mirror is in the X-ray beam. The light bulb is off to the side, so we won't cast the light bulb artifact on every image that we shoot. So it goes through that as well. Now I'm going to even both of these up, and I'm going to make it more like each other. So we've got that. And that is what we refer to as our BREMS spectrum. All right, so this is our emission spectrum. The creation spectrum is what gave us all those low energy X-ray photons. That's at the target. This is after it comes out of the housing. This is what we expose the patient to. Much safer, but notice that in all that, the only thing that we really changed by running it through all that filtration was eliminated low energy X-ray photons. Peak energy is only controlled by kVp. All right, nothing else. But what else does kVp control? Well, we got more penetration, so we have a higher. Yeah, if we don't do anything with our mass, we're going to have a higher dose. But since it increases our penetration is our quality, right? So it increases our quality. It gives us our characteristic spectrum, and it gave us all these increase in numbers, which again gives us higher dose, providing we don't do anything else with it, right? If the only thing that we do is increase kVp, we increase dose. Yep.
So I'm trying to wrap my head around, when we say a higher quantity for the kVp, is that just saying higher quantity that gets the IR?
Well, it's eventually, yes.
Yeah.
All right. So, and that's a very good question. So, and without getting too deep into it, because I'd have to go back and do all the math. What you get when you increase your kVp by 15% is a 15% increase at the image receptor. Okay, or I'm a doubling of the dose of the image receptor. increase 15%, we get a doubling of the dose of the image receptor. The patient dose does not go up by 100%. Because we'll get more penetration.
Right.
It may go up by, just spitballing numbers, 80%.
Mm-hmm.
So it's still significant, but the most significant increase is at the image receptor because of the increase in penetration.
Yeah. So it's all bang for buck.
Yeah.
Yeah.
Yep. Yep. Now, back in the day of screens and films, just to give you kind of historical perspective and why I say it's harder for you to wrap your mind around, is that if you did this, and this is the only thing that you did back when we used films, then you'd see two things. And that would be, because we have so much of an increase in numbers, then our image would turn out a whole lot darker. All right, so let's say we make the perfect image and we increase our kVp by 15%. Our new image would be too dark. That's number one. Number two is that because we get an increase in penetration, all tissue types will be penetrated more. Right? The thing that makes bony X-rays pleasing to the eye is a contrast between the dark portion of the image and the lighter portion of the image. Does that make sense? Okay, so if we increase our kVp though, we get more penetration of the bone as well. So more of your tissue types are penetrated more evenly, and what we would get is not just a darker image, but those bones would be kind of washed out. Immediate feedback. Ooh, I screwed this up. Try this in clinicals. I don't mean on a patient. Please don't do this on a patient just to see what happens. But find something that you can kind of mock up as a patient. Some of your clinical sites will have skulls. We just don't have it in a budget to have a skull everywhere, but you can mock up take your tennis shoes off. Most of your tennis shoes now have air cells in them, which gives you a contrast. You're not going to make your tennis shoes radioactive or anything. This is ionizing radiation. This is not radioactive. But those air cells give you some good contrast. You can see where the air is. You can see where the rubber is. You can even see the Nike swoosh if, in most cases anyway, if you're wearing Nikes or whatever. Take them off and take an image of them. And then increase your kVp by 15%. Shoot it again and see what happens. See if you can tell a difference between the images. Probably not. Increase your kVp by 15%, reduce your mass by a factor of 2. Shoot it again. You'll have 3 images that almost look identical. So it's not easier for y'all. It's harder just in a different way. Or it's as hard just in a different way. Because you can't see the results and what's happening inside of the patient, the result on the image receptor, because the computer fixes it, makes everything look pretty. That's great, for a repeat, on a repeat basis in a radiation safety, dose reduction factor for the patient, but really for learning, for you to understand what's going on inside of the patient. It's kind of murder. You just can't see it. Right? So any questions on kVp specifically in this context? No? We will pick up there on Wednesday.